Okay, for number 4, we got particle moving along the x-axis. The velocity from 0 to 6 is given by the differential equation above. So we have a picture of the velocity function. We know the velocity at 0 is 0. It's also 0 at 3 and 5. We can see it crosses the x-axis there. And the graph has horizontal tangents at 1 and 4. And the areas of the regions bounded between the t-axis and the graph of v on the intervals of 0 to 3, 3 to 5, and 5 to 6 are 8, 3, and 2. And time 0, the particle is at x equals negative 2. So ultimately, in the part A, they want us to do between 0 and 6, find both the time and the position of the particle when the particle is going to be furthest to the left. Okay? So when it's furthest to the left, so keep in mind that a couple ways to think about that, but if we have our picture of our velocity, we know that we're accumulating from 0 to 3, we're accumulating negative area, okay, which would indicate a leftward direction, if you will. And then we're accumulating positive area here, which would be rightward direction. And then from 5 to 6, we're going negative again. Okay? So keeping in mind that when we have our closed interval here from 0 to 6, if we look at f of 0, if you will, we know f of 0, it's negative 2. That's our position. Okay? And we know that there's going to be changes in direction at 3 and 5 because that's where the velocity is equal to 0. So at f of 3, we'll have accumulated negative 8 in terms of area. So that means our new position will be negative 10 because we were at negative 2 and we accumulated another negative 8. So that would be our position. And then once we get to 3, then the velocity becomes positive, which means we're moving back towards the right. And from 3 to 5, we're gaining 3, which means that we'd be at negative 7 when we're at 5. And then when we go from 5 to 6, we're gaining more negative area, which means, and then we're gaining 2 more in the negative direction, which means we'll be at negative 9. All right, so letting those be our positions, if you will, then we're leftmost when we're at that spot. And we're at time 3, we're at negative 10. And ultimately, again, the question says find both the time and the position of the particle when the particle is furthest to the left. All right. So if we use our candidate test, we can see that this is the answer. The time is 3. So at time 3, our position x of t is negative 10. All right. So with that analysis, we should add 3 points. 1 for identifying the 3 as a candidate, and because of the fact that it's where we change directions, that'd be one of our changes of directions. Considers the area between 0 and 6. So we've considered area by doing this. So if we, basically found the answers to all of our candidates, we got another point. And then our conclusion, we add another point. Questions on part A? Alright, let's see what we got here for part B then. It says, for how many values of t between 0 and 6 is the particle at x equals 8? Explain your reasoning. Okay. So, again, remember what we've done here with our, and I called it f over here. I guess I probably should have called it x if I'm stay consistent here. So we'll call it x of t. We went from position negative 2 to position negative 10. Okay? And knowing that, that x is a differentiable function here, okay? What does that tell us about what happened between negative 2 and 10 here? Between 0 and 3 at some point we must have crossed negative 8. Okay? And what theorem guarantees that? We want to get all the points here. What? Yeah. So don't lose points by not knowing the name of the theorem. Okay, intermediate value theorem guarantees that if we go from 0 to 3 and we go from y value negative 2 to y value 10, that we cross the line x equals negative 8 at least once. Okay? And what happens if we go from negative 10 to negative 7? Cross it again. And negative 7 to negative 9? Cross it again. So bottom line is how many times do we cross it? And it says for how many values of t is the particle at x equals negative 8? We know that the answer here is 3, of course, because again, our analysis here because of the intermediate value theorem. Okay. One thing that we also know too is that looking at our graph, we know that we're essentially our velocity remains negative from 0 to 3. Okay. So if the velocity is negative going from 0 to 3, can there be any more than just that one time that we hit -8? Remember, our velocity, that means our function is decreasing from 0 to 3. True? So could there be more than just that one time when it hits -8? Same thing here. It stays positive from 3 to 5, so could it cross the -8 line any more than just once? No. So really, instead of at least 3, the answer here in this case, knowing that we have this velocity curve, the answer is actually is exactly 3, isn't it? Instead of at least 3. Alright, so intermediate value theorem guarantees that since x of t is continuous, and again using our above chart, okay, we go on 0 to 3, we go from y equals -2 to y equals -10, okay, decreasing from -2 to -10. Okay. That means that we must have crossed y equals -8. Okay. And we can get the same analysis for the other intervals, 3 to 5 and from 5 to 6. And ultimately, 3 points here, okay, identifying, and we want to do that for all these. We want to identify from 3 to 5 and from 5 to 6. Okay. So we're decreasing here through -8, and then of course this part we're increasing from y equals -7, or excuse me, -10 that is, to -7. And then again we're decreasing y equals -7 to -9. Alright, so ultimately all that information that we'd write here, invoking the intermediate value theorem, talking about the fact that it's a continuous function, we're going through from one y value to another, where that -8 is between. Okay, ultimately all that stuff is worth 3 points. Break it all down. Okay. The next part here says on the interval on the interval 2 to 3, it says the speed of the particle increasing or decreasing. So is the speed of the particle increasing or decreasing? So keep in mind that on that 2 to 3 interval, we're going from here to here. Right? Right? So remember, this is a picture of the velocity. True? How could we make this a picture of the speed? Absolute value. And what's that going to do to this part of the curve? That's going to make it go up here, isn't it? So that's actually our speed curve. And so remember the question here is the speed of the particle increasing or decreasing? What's going on with the speed? Yeah, it's decreasing. Okay. So we'd say speed is decreasing. Okay. Alright, and the reason here is since the velocity is negative and increasing. Remember, whether I do this velocity, whether I do it with the velocity being concave up or concave down, even if it looked like this, if I flip that, it would still be decreasing if it were a speed. So either way that curve was worked, we know that since we have speed being the absolute value of the velocity, right, if we were to absolute value that piece when the velocity is negative and it's increasing, we know that our speed is going to be decreasing. 1 point for that part. Alright, and let's see if we can go with part D here. Part D, they ask us during what time intervals, if any, is the acceleration of the particle negative? Well, we can see the acceleration of the particle because it's the slope of our V curve, so from 0 to 1, the acceleration would be negative. And from 4 to 6 would be negative. And the justification would be because V prime is less than 0. The derivative of v is negative. And what do we know about v prime? V prime is the same as what? Same as a, it's acceleration. 2 points, one for the right answer, one for y. And again, you could say this in words as well if you want to say that the derivative of the velocity is negative on those intervals. Something like that would be fine as well. The velocity is decreasing, another way to say it. Alright, questions so far? Alright, let's check out 2005 then, see how we did. 2005, 2008 still. Number 5. Number 5, we have a derivative function given here that tells us that f prime is x minus 3 times e to the x for x greater than 0. And we know that f of 1 is equal to 7. Given information for us. And again, we're dealing with only x is greater than 0 at this point. Alright, so the first part here in part A says the function f has a critical point at x equals 3. At this point, does f have a relative minimum, maximum, or neither? And justify. So in part A, we know that there's a critical point because if we set the derivative equal to 0, 3 would obviously be a solution to that. So 3 is our candidate that we want to look at here. So let's see what would happen if we put in a 2, let's say. If we put a 2 in here, we'd have 2 minus 3, that'd be negative. And if I did e to the 2, that would be positive. And so that means that spot would be negative. If I put something to the right of 3, like 4, I would have positive here, positive. So, and again, make sure we label the number line as f prime. And what does that tell us? That 3 is a what? 3 would be a minimum. So at x equals 3, and they ask us at this point, does it have a relative maximum, minimum, or neither? So at x equals 3, we'd have a relative minimum. And our justification is our work is here. Say that ultimately we're decreasing to the left, increasing to the right. Makes a minimum point at x equals 3. Alright. And in part B, it says on what intervals, if any, is the graph of f both decreasing and concave up? Alright, well, bottom line here is we know that the graph of f is decreasing anytime that the derivative is negative. So ultimately, anything left of 3 here, since 3 is the only critical point, because e to the x is not going to have any spots where it equals 0 or doesn't exist. So therefore, 3 being the only critical point means we're decreasing all the way till we get to 3. Okay? So the only other issue then is on what intervals is it both decreasing and concave up. So we're going to need the second derivative here. So if we go ahead and find the second derivative, we do the first times the derivative of the second plus the second times the derivative of the first, we'd have that as our second derivative. And these two both have an e to the x in common, so I'd factor that out. I'd be left with x minus 3 plus 1. And then we'd have e to the x be x minus 2 instead of minus 3. And it would equal 0 at 2 then. We set those two equal to 0 and solve. And so looking at our second derivative, see if we have a change in concavity at 2. And we look at our second derivative here again. If we put, say, let's see. So if we put a 1 in here, okay, this is going to be negative, and ultimately it's going to be negative 1, so it's going to be negative e to the 1. Oops, not a 1 in there, a 2. I don't want to put a 2 in there. If I put a 2 in there, I'm going to get 0. So I want to put a 1 in there instead. So ultimately this is going to be negative 2, e to the 1. And this is going to be plus e to the 1. So ultimately we'd have negative e. So our answer if we put in a 1. So that means that would be negative. And if I put something bigger than 2, like say 3, 3 would give me 0 here. And give me e to the 3 here. It would be positive there. So that's my analysis there. So that means I'm concave up on 2 to infinity. So if I look at these two number lines together, okay, where am I both decreasing and concave up? Would it be on anything bigger than 2 but also less than 3? So it would be between 2 and 3. Would be the result. Alright. So ultimately 2 points here. You got there was actually 3 points. 2 for finding the antiderivative and 1 for the analysis. Space here, I think, for that last part.
How much was A worth?
A was worth 3 else, or 2 actually. A is worth 2. You got yeah, I guess both of these parts together. I mean, the fact that you said that it's a minimum, and the fact that you showed your justification. So 1 for each of these 2 parts. All right. And last part, then we have part C. This is find the value of f of 3. So we're looking for f of 3. And again, we know that the derivative here is x minus 3 e to the x, and we know that f of 1 is 7. So we got a couple of choices here. Remember, one thing that that we know is that this is in the non-calculator part. Keep that in mind. So we have a non-calculator problem, and this is why this part of the problem is why this is on the BC test, because we can see here that this U substitution is not going to work, and we have a multiplication, so it's going to be integration by parts. Okay, so that's why it's a BC problem. This wouldn't have been on the AB test today here. Okay, because and you know that one thing that we can always do too is with our initial condition, we could write from 1 to t of x minus 3 e to the x dx plus 7, and have that be our antiderivative function. Okay, and then just put a 3 in there and do the math. But the problem is it's a non-calculator problem. If it was a calculator problem, then we would just write that integral expression, put in 3, and calculate. But seeing as though it's a non-calculator problem, we can't do that. So our only option here then is we got to anti-differentiate. We actually have to find the function f and then plug in 3. Okay? But knowing that my x minus 3 and e to the x is my integrand on 1 to 3, and if I let my u equal x minus 3 and my dv equal e to the x, my du would be simply dx, and my v would be e to the x. And so they gave us a pretty easy function to work with here, two easy functions to deal with. Easy to find the derivative and integrate. And so remember, our integration by parts is uv, so that would be e to the x, x minus 3, minus v du, e to the x dx, which again is easy to integrate. E to the x, x minus 3, minus e to the x, and then that is all to the 1 to 3 limits. Well, 3 in here we know is going to give us 0 in that part, and then negative e to the 3 here. And if we put a 1 in there, we're going to get negative 2 e to the 1 minus e to the 1. So we'll have negative e to the 3. And then in here we're going to have negative 3e. It's going to be minus minus, so it's going to be plus 3e. Alright. Alright. And oh, I forgot this. Yep. We also remember we have that integral has a plus 7 on the outside of it. So remember when we calculate this part right here, and we're calculating the accumulation, if you will, between 1 and 3. We're already at the value of 7, so not only do we have to have that accumulation from 1 to 3, we also have to have the 7 plus. So really it'd be 7 minus e to the 3 plus 3e. Alright, 2 points for doing the integration by parts correctly. 1 point for making sure you recognize that the 7 has to be part of it, that we're adding a 7 to whatever we get when we do the integral. And then the final answer, the other point, 7 minus e to the 3 plus 3e. So we're just doing the integration by parts correctly, having 7. So the fourth point is. Questions on the breakdown on that one, or anything about the integration by parts? one then. We got a logistic differential equation given. And that logistic differential equation is y over 8 and 6 minus y. So that's our differential equation. F of t is the particular solution to this differential equation, and we know that f of 0 is 8 for us. So, on our first part here, on part A, we had to draw a slope field. And it said a slope field for this differential equation is given below. Sketch possible solution curves through 3, 2, and 0, 8. Okay? I won't attempt to redraw that because they already have one here that you can look at, and it's much nicer than what I would draw. So it's my bad art. But bottom line here is if we go through 0, 8, we can follow the trend here. And we can see that since this is horizontal here, we should expect some kind of horizontal asymptote there at 6. Okay? If it goes to that point 3, 2, and again we follow that curve structure, okay? And those should be our two. Ultimately, 2 points. If you got those two at least close to that. And again, I don't know how real picky they are on that, but you know, you need to have something that at least A goes through the point and B follows the curves, you know, fairly appropriately, I guess. Questions on how they got either of those two? Alright. Part B says use Euler's method starting at 0 with 2 steps of equal size to approximate f of 1. So remember, here's our initial point here, f of 0. Zoom back out. So our initial point here is f of 0 equals 8. And we want to do Euler's method. So if we want the next approximation, which would be f of 0.5, so they told us to do 2 steps. Remember, that's going to be equal to the initial y value plus the derivative times the change in x. So that's going to be our general setup. So initial y value, derivative at the point in question times the change in x. And so our derivative, remember, is this. And so what is it that we're going to put in here? Well, this only depends on y. And what's y? Y is 8. So I'd have 8 over 8, which is 1, and then 6 minus 8, which would be negative 2. So we'd have negative 2 here. And that means our guess for f of 0.5 using Euler's method, which is, again, just a iterated process of linearization. We're just writing a linearization for this function at that point. And with that said, we'd get, what, 7? And then if we want to go to f of 1, now we need to go to have our 7 plus something times 0.5. And remember, the something that goes in here is the derivative at the new point, which is, keep in mind, the new point is 0.57. Now, in our case, that 0.5 doesn't really matter because the derivative here doesn't depend on x. It just depends on y only. So if I put my y of 7 in there, I'm going to get 7/8. And then times negative 1, 6 minus 7. So it'll be negative 7/8. And ultimately that'd be 7 minus 7/16. So half times 7/8. And if I do the math on that, we're going to get 6 and 9/16. And ultimately 2 points. The Euler's method structure here is worth a point. And then the final answer is worth a point. So that right there is worth 1 point, getting 6 and 9/16. Or you could have it as an improper fraction, of course, too, 105/16. Questions so far? Okay. The next part then says write a second degree Taylor polynomial for f about t equals 0 and use it to approximate f of 1. So if we're going to write a Taylor polynomial for this function f in question, we know that it's going to come from f of 0 equals 8 first, which f of 0 in this case is 8. F prime at 0. The derivative at 0, remember the derivative is defined above. Okay. So what would be the derivative at 0? nope. At 0, remember, don't put a 0 and oops, I'm pointing at the wrong one. Remember, we're not putting a 0 in here because this is determined by y, right? But we still want f prime at 0. So what's the y coordinate? Or the y coordinate's 8 here, 0, 8. So at 0, our derivative would be 8 over 8. 6 minus 8 would be negative 2. So we'd have negative 2x then. And then our second derivative at 0. If we do our second derivative at 0, we need to actually find the second derivative. We don't know that. Okay. Alright. So, question is, how do we find that second derivative? Well, we know that dy dt is equal to y over 8, 6 minus y. And if we want to find the second derivative, which is d squared y dt squared, then you got to keep in mind this is all relative to t here. It's a function in terms of t. So we have essentially we'd have a product here we'd have to recognize if we want to find the second derivative of that. So our product would have y minus 8, and then our derivative of the inside here, the derivative of negative y would be negative dy dt. And then we'd have 6 minus y, and then we'd have 1/8 dy dt. We do the product rule there. Again, taking the derivative of that with respect to time. And let's see if we can fill in our blanks here. What do we know about y? And keep in mind we want the second derivative at 0. So at 0, what's our y coordinate? 8 again. So we had 8 over 8 here. What about our derivative at 0? Our derivative at 0 was negative 2, wasn't it? So that means that right there would be a 2 because we have a negative, negative 2. And then 6 minus 8 would be negative 2 again. And then 1/8 times negative 2. We filled in all the blanks. And so ultimately we'd have 2 out of this one plus this whole thing would be 2 times 2 is 4. 4 times an eighth would be a half. So we get 2 1/2 or 5 halves. So 5 halves would be our second derivative. And remember that's going to be x squared over 2 factorial. So final answer then would be 8 minus 2x plus 5x squared over 4. Okay, points. If you found the second derivative, which is this, you got 2 points. If you differentiated that on the second derivative of dy dt, the derivative of dy dt, I should say. And the 1 point for getting the stuff in the right spots. Function, derivative, second derivative. So we made your Taylor polynomial. And then there was one more question it asks us here to just to estimate f of 1. So again, this is our f at this point. If we put a 1 in here, we're going to get 8 minus 2, that's 6. 6 plus 5 fourths would be 7 fourths. Or 7 1/4, I should say. Another point for getting the approximation. Okay. Questions? It doesn't ask you here, but which of these would we expect to be more accurate for f? B or C? 6 9/16 or the 7 1/4? Keep in mind, what is Euler's method based on? It's based on linearizations, right? Okay. So we're using linear functions to calculate. And what are we using here with our Taylor polynomial? What? A quadratic. Every time we make a bigger degree, it should be more accurate, shouldn't it? Okay. So if we used a cubic, it would be even more accurate, and so on. Alright. Then the last part here says, what's the range, if t is greater than 0, what is the range of our f function? Let's go back to the slope field here. Keep in mind that, that one of these two curves is the right curve, knowing that we know f of 0 has to equal 8. So which curve is the right curve? Top one or the bottom one? Remember, these are both possible solutions depending on the initial condition. Okay, obviously the whole thing is not a function because there's wouldn't pass the vertical line test. But again, which one is the one that we were worried about? It's this one. True? So what would be the range? With t greater than 0, what would be the highest this function gets? Highest it gets is 8, isn't it? And what's the lowest it gets? It'd be 6. So the range would be from 6 to 8. So why don't we have to worry about this piece? Because it doesn't satisfy the initial condition. That's not our curve. Our curve is the top curve. So it goes from 6 to 8 would be your range, and that's worth one more point. You got the 6 to 8 part. Keep in mind that it should be also including 8, because we actually get to the point 0, 8. Okay. 6 being an asymptote, do not actually get to 6, so we would not want to include that. Questions on anything about